YAML. Canonical correlation analysis. Description. Canonical correlation analysis (CCA) is a statistical method that aims to find linear combinations of two sets of variables that have the highest possible correlation. It is particularly useful for understanding the relationships between two sets of variables that may be correlated but not directly comparable. Algorithm. CCA seeks to find a set of canonical variates linear combinations of the original variables for each set, such that the correlation between corresponding canonical variates is maximized. This process involves finding the eigenvectors of the cross-covariance matrix between the two sets of variables. The canonical variates are ordered by decreasing correlation, and the first few canonical variates typically capture the most important relationships between the two sets of variables. Use cases. Discovering relationships between different types of data, such as gene expression and clinical data. Analyzing multivariate data to identify common patterns across different variables. Reducing dimensionality of data by projecting it onto a lower dimensional space defined by the canonical variates. Predicting one set of variables from another set of variables based on their correlations. sklearn implementation. The sklearn cross-decomposition CCA class implements CCA in scikit-learn. It provides methods for fitting the model to data, transforming data into canonical variates, and retrieving the canonical correlations and loadings. Parameters. Name n components. Description: the number of canonical components to extract. This determines the dimensionality of the transformed data. Type int. Default to. Name scale. Description: whether to scale the data before performing CCA. This is generally recommended to avoid issues with differences in scale between variables. Type bool. Default true. Name copy. Description: whether to copy the data before fitting the model. This can be set to false to save memory if the data is not going to be modified. Type bool. Default true. Attributes. Name x loadings. Description: loadings for the first set of variables x. These represent the weights applied to the original variables to obtain the canonical variates. Type array-like. Name y loadings. Description: loadings for the second set of variables y. These represent the weights applied to the original variables to obtain the canonical variates. Type array-like. Name x weights. Description: weights used to transform the original variables in the first set x into canonical variates. Type array-like. Name y weights. Description: weights used to transform the original variables in the second set y into canonical variates. Type array-like. Name correlations. Description: the canonical correlations between the corresponding canonical variates. Type array-like. Methods. Name fit x, y. Description: fits the CCA model to the given data. Name transform x, y. Description: transforms the given data into canonical variates. Name fit transform x, y. Description: fits the CCA model to the given data and then transforms it into canonical variates. Challenges. Description: data scaling. CCA is sensitive to the scale of the variables. It is generally recommended to scale the data before performing CCA to avoid biases caused by differences in scale. Fix: use the scale true parameter in the CCA constructor or manually scale the data using a scaler. From sklearn, preprocessing. Description: number of components, choosing the appropriate number of canonical components to extract is important. Too few components may not capture all the important relationships, while too many components may lead to overfitting. Fix: experiment with different values of n components and evaluate the model's performance on a Held out validation set. Description interpreting results. Interpreting the results of CCA can be challenging, particularly when dealing with a large number of variables. It is helpful to visualize the canonical correlations and loadings to understand the relationships between the variables. Use visualization tools, such as scatter plots and heat maps, to visualize the canonical correlations and loadings.